We're now ready to calculate the one-sample t-test and the t-interval. So it's a very good idea to use the one-sample t-test or calculate a t-interval when we don't know the population standard deviation sigma, or we don't know that the population is distributed normally, preventing us from really estimating the population standard deviation using the sample standard deviation S, or when the sample size is pretty small, say less than 30 observations, preventing us really from reliably estimating the population standard deviation using the sample standard deviation S. So in general, we use the one-sample t-test or t-interval much more often, and it's the default for much of the statistical software that we use. The t-distribution model, the sampling distribution, looks like this. So you have these different t-values above or below 0. The distribution is centered on the population mean, or the claimed value of the population mean, and it has a spread. But the idea is that the shape of the distribution changes depending on the sample size. In general, with a smaller sample size, you're going to have greater uncertainty. You're more likely just through random chance to have an extreme sample mean above or below that population mean. And so the peak of the distribution lowers, and the tails are what we call fatter. They're kind of a little bit larger. So you're more likely with the t-distribution to have, as a model of the sampling distribution, to have extreme sample means above or below. And this just reflects the fact that realistically, right, with a smaller sample size, the sampling distribution will look more like the t-distribution than it does the standard normal distribution. Right? So there's been a computer revolution, right? With modern statistical software, computing p-values, test statistics, and confidence intervals are very easy to do. So historically, researchers and statisticians have focused a little bit more on the standard normal distribution, but with modern software, the t-distribution and using the t-distribution is pretty easy to do. But we're going to use statistical software to calculate t-values and probability values using the t-distribution rather than probability tables. Right? The key point, though, it's important to understand the mechanics of hypothesis testing and test statistics. But most researchers today focus on p-values and confidence intervals. Let's think about why the p-value is so powerful. Right? It makes hypothesis testing easy. They're usually obtained from statistical software, and they adjust for large or small samples and for one- or two-sided tests. So you don't have to worry about any complicated issues with the p-value. All you need to do is interpret the computer output and remember the mantra. If the p is low, the null must go. Right? What's great about the p-value is all you need to know is something about the hypothesis test. You know, what's the null, what's the alternative, and then all you need to know is the p-value. And then you can make an easy interpretation. Okay? Depending on the level of alpha you use, you can use that p-value, or probability value, to make a conclusion. You can even use various levels of alpha for a given p-value. Suppose your p-value is 0.025, and you can compare that p-value of 0.025 to an alpha of 0.01, 0.05, 0.1, and you can report a range of results. So the p-value is very powerful. It's very commonly used in inferential statistics, and especially when we work with additional hypothesis tests besides the ones we're discussing right now. The p-value is a very convenient way of making decisions. Once you understand p-values, okay, the idea is you can interpret any hypothesis test if you're given the null and the corresponding p-value. Right? And again, the p-value just tells you the probability of obtaining a test statistic as a more extreme than the one you actually obtained under the assumption that the null hypothesis is true. Right? Really, and I would say most researchers skip the underlying mechanics of hypothesis testing and focus on the p-values. Right? We do want you to focus and understand what's going on with hypothesis testing and the idea behind test statistics. But in some instances, particularly when we work with the t-distribution, we will focus a little bit more on understanding p-values. The confidence interval is also very powerful and commonly reported in actual research articles. Confidence intervals, they can make hypothesis testing easy, especially in the context of two-sided hypothesis test. So all you need to interpret the output from a confidence interval is that if the null is out, then it's in doubt. Okay? To put another way, if you have a null hypothesis that the population mean is 0, right, versus the alternative that the population mean is not 0, and the 95% confidence interval is from 0.2 to 3.4, then you can reject the null at the 0.05 level. Right? That's because that interval, right, does not include that claimed value of the population mean. It does not include 0. To put another way, if the null is out, then that null is in doubt, or it's in doubt. So the idea is that you can interpret a confidence interval, a traditional confidence interval, as equivalent to a two-sided test. So p-values and confidence intervals really can make this hypothesis testing quite easy to interpret. So let's go through these examples of using the t-test. Right? The t-test is similar to the z-test. They're preliminaries. You should state the target population parameters of interest. So again, we're interested in the population mean. And then we have several steps. Right? First, you state the null and alternative hypotheses in terms of H subscript 0 and H subscript A. Then you select the significance level. Traditionally, we pick 0.05. Then you compute the test statistic T. Right? We will use statistical software to help us interpret and calculate the test statistic T. Then what you do is you assume the null is true. To put another way, you assume that the sampling distribution is centered on that claimed value of the population mean. You say, okay, well, this person is claiming the population mean is, say, 37. Right? All right, if the population mean is centered on 37, all right, let's compare that to where our data lie. If it's really inconsistent, then we can reject the null. It's because it's so unlikely under that assumption that the null is true that we would actually obtain the data, in fact, we have obtained. So formally, we assume the null is true, and we make a decision by either comparing the test statistic we've calculated with some critical value based on alpha, or we compare the p-value with a significance level of alpha. So if the p-value is less than or equal to alpha, then we reject the null. If the test statistic lies in a critical region on the t-distribution, then we reject the null as well. Then what we do, using either 4a or 4b, we state our conclusion, focusing on the statistical significance, whether we rejected or failed to reject the null, but we also want to focus on the substantive findings. What are the implications of this research? And then, of course, I always highly recommend that you calculate a confidence interval to help us understand what's going on. So keep in mind, all right, in most applications that use the null, when you're making inference about the null, they use the t-distribution model as the default. Right? So again, nearly all modern statistical software is going to use the t-distribution as a model for the sampling distribution. The reason is that the standard normal distribution model works best only when the underlying population distribution is known to be normal, you know the population standard deviation sigma, or the sample size is pretty large. Right? The great thing about the t-distribution model is that it's more realistic. It's a more realistic model of the sampling distribution when that sample size, right, is quite small. That's because the t-distribution takes into account that you're more likely to gather an outlying sample with a small sample size. Those sample means are going to bounce around on the sampling distribution a lot more with a small sample size. Right? And with that, we're going to go through a few examples of actually going through the steps of calculating a one-sample t-test for the sample mean.